All right, so our topic today is improper integrals. So that is like your title. And this is a 2-day topic. We're going to spend 2 days on this. So an improper integral, probably like, what on earth is that? It's an integral where one or both boundaries is infinite. That's one option. One or both boundaries are infinite. So you would have integral from like 2 to infinity. Okay. And the other like way that it can be considered an improper integral is if the function has a vertical asymptote. So that would be something like, here's your graph of 1 over x. Like if it looked like this, and you were trying to do an integral from like here to here, do you get what I'm saying? And there's that asymptote in between, that would be an improper integral. So we are going to do these ones today, and then we're going to do these ones next time. It's going to be a 2-day topic. So I put the definitions on this sheet here. So if you want to look at the front side, these are the ones we're going to do today. And it says infinite limits of integration. So we're going to have like an integral from something to infinity. The ones on the back, the infinite discontinuity. Infinite discontinuity means vertical asymptote. That's what that means, vertical asymptote. We're going to do those ones next time. So it'll be a 2-day topic, but that's what infinite discontinuity means. So I'm going to draw a little picture for each of these because I think a picture helps a lot with understanding like what's going on. If a function is continuous from a to infinity, so for example, if it looks something like this, and then here's a, then the integral from a to infinity would be this area. So it's your integral from a to infinity. And the way we write it, and I know this is really small, but you guys have it there in front of you. What you do is you basically move the problem. Like if the problem is that that part of the integral is infinity, you just take it and put it outside of the integral. You do limit as b goes to infinity and then put a b there instead. You basically just like shuffle the problem outside of the integral. The same thing is going to happen going the other direction. If f is continuous from negative infinity to b, so you would have something like this. And then like here's b. Then your integral from negative infinity to b would be this area. And you do the same thing. Change the, and we usually use a for the lower boundary and b for the upper boundary. Frankly, I don't care what letter of the alphabet you use. You can use whatever letter of the alphabet you want, except for x, okay? I'm gonna stick with a for the lower boundary and b for the upper boundary. But you just do limit as a, oh, that should be an a. I'm so sorry. Is that a z there for you? I'm so sorry. Oh, yours says a? Oh, I must have fixed yours, but not mine. A. I apologize. Although, like I just said, the letter of the alphabet doesn't really matter that much, but that should technically be an a. Limit as a goes to negative infinity, and then you make the values a to b. Okay. Does anyone else think that that's kind of cool that you can get that area though? I mean, like I know doing the problems isn't super fun, but that does kind of geek me out. But there would have to be a horizontal asymptote there. You get that, right? Like it has to level off somewhere. All right, and then here from negative infinity to positive infinity. So that would look something like this. And you would be getting that entire area. That is kind of cool. I mean, that does like geek me out a little bit. Like, hey, we can find that entire area. Then what you're going to do is split it. So you would do from negative infinity to something plus something to infinity, where c is any real number. If you get to pick what number, pick 0. Does that make sense? Like if you get to pick 0. And then you would do each of those integrals like these. Okay. The improper integral converges if you get an answer. If you get an answer, great. If you don't get an answer, like it goes to infinity or something like that, then it diverges. So you would just say diverges. That's like your no solution. All good? Now we're just going to do a bunch of problems, okay? Where'd my blank piece of paper? There it is. All right, I'm going to write out steps for these. If you're like a steps person, like, hey, Ms. Cole, I really just want to have steps to do this, then you can write this down. If not, then just like pay attention. First thing you're going to do is set up the limit and fix the boundaries. And that's where you move the infinity out of the integral. Like it would be limit as b goes to infinity, and then you would put a b as the boundary instead. So you basically like set up the problem. And then because it's an integral, you're going to do the antiderivative. That's no different than we've done before. I'm not changing what an antiderivative is. It's still going to be the same. You're going to do upper boundary minus lower boundary. That's your fundamental theorem of calculus. Again, I haven't changed that. That's all that part of the problem stays the same. You're just going to have this limit out front. It's going to be a little bit of writing. Okay, you're going to write the same thing over and over, so it's a little repetitive. And then the last thing is you're going to evaluate the limit. So that limit is going to like sit out front the whole time, and then at the very end, the last step, you'll just evaluate the limit. And finally, we get to like actually do an example. Everything makes a whole lot more sense once you see an example, but I do have to explain all that first so that it'll actually like make sense, hopefully. So what makes this improper is the fact that there's an infinity as one of your boundaries. So we're going to do limit as b goes to infinity. I picked b because it's the upper boundary. Again, I'm going to stick with a for the lower one and b for the upper one. Again, I don't care what letter you pick. You just can't use x, that's all. Limit is b goes to infinity, and then it will be integral 1 to b of this. Now, how can we rewrite that? X to the negative second. And now you're basically just going to do the problem as before. Antiderivative, upper boundary minus lower boundary. You just annoyingly have to write this limit out front every step. I won't take off if you don't, but it worries me that you'll forget to do the limit at the end. If you don't, it's not that big of a deal to write limits, so I would say just do it. All right, antiderivative. You would have to add 1 to the power. So that would make it -1. And then you divide by -1, so you'd have a negative out front. How can we rewrite that so it's a fraction? Okay. -1 over x such that 1 to b. And now we're on this step 3. We're going to do upper boundary minus lower boundary. Again, you got to write the limit out front or not. I mean, again, it's up to you. I'm going to write it every time. Upper boundary minus lower boundary. So if you plug in b, you're just going to have -1 over b. And if you plug in 1, you're going to have -1. And then your last step is you evaluate the limit. So as b goes to infinity, what are we going to get for this first part? 0. If the denominator gets infinitely large, and you're going to see those a lot because that's pretty much how these turn out. The denominator gets infinitely large, you get 1 out of a gazillion, which is going to go to 0. These negatives cancel. And the answer is 1. That area under the curve is 1. That's cool. I can disagree, but that's cool. I think that's neat. All right, let's try another one. Or questions? Did that go okay? No one really said anything. Were we just all right? Okay. So again, what makes it improper is the fact that there's an infinity in there. But you basically just move the problem. Like if the problem is the infinity, you just move it out front. So it's going to be limit as b goes to infinity, integral from 1 to b. You're basically just like renaming it. Like, oh, we didn't like calling it that. Let's call it something else. 1 over x dx. And then step 2, you're going to do the antiderivative. So what is your antiderivative for 1 over x? ln of x, perfect. Such that 1 to b. All right, now we're on the third step. We're going to do upper boundary minus lower boundary. So that would be ln of b minus ln of 1, 0, good. And then the last step is evaluate the limit. Ln of, you can't do ln of infinity, but as you go to infinity, ln is going to go to infinity. So you end up with infinity. This is what your ln graph looks like. You guys remember this, sort of, vaguely? Like this graph is going to keep going upwards forever. So you get infinity, so it diverges. It means you can't get an answer. So like, again, what it is the area under the graph. And it means it won't level off to a certain answer. I don't know how to say that any different. Like that leveling off behavior, because that graph does have a horizontal asymptote, but the way it works out is when you keep on going forever, you keep adding more and more area, and so you're never gonna get a complete answer. No, you still wouldn't, because 1 over x is symmetric, so it would happen the same in both directions. Yeah, so you still won't get an answer. And actually, I'm gonna do one more example, and then I'm gonna show you kind of a pattern for that. Or not a pattern, but sort of like a rule. That's to the 5th. 1 to infinity, 1 over x to the 5th. All right, so it would be limit as b goes to infinity. Again, it's not hard, it's just repetitive, and it's a little bit of writing, okay? Integral from 1 to b, and I'm gonna write that as x to the negative 5th dx. And so you would have to add 1 to that power. So it would be x to the negative 4th, and then you need a negative 1/4 in front of that. I tend to just do that like off to the side, like kind of scratch work. And then when I put it in the answer, I can fix it. How can we write that so that I can fix the negative power there? Four x to the 4th, good. Such that 1 to b. And so now we're on the 3rd step, upper boundary minus lower boundary. So if you plug in b, this is going to be the same thing, just with a b in there. It would be negative 1 over 4b to the 4th minus, now if you plug in 1, you will just get negative a 4th. And your last step is to evaluate the limit. So as b goes to infinity, again, this denominator will get infinitely large. So what does that part go to? 0 plus a 4th, and so you get a 4th. So again, the area under the curve is a 4th. It's neat. It came out to a 4th. That's so cool. All right, so let me show you a little pattern for this, just to like kind of tie all those together. If it's from 1 to infinity over 1 to infinity, 1 over x to a power. We put p for that power. This is called a p series. The reason I'm bringing this up now is we're going to do a lot with infinite series. There's 2 whole units on nothing but infinite series. Okay, and p series is one of the ones that we're going to look at. So I'm bringing it up now, and then later on you'll be like, oh, I remember that, hopefully. All right, it's going to come out to 1 over p minus 1 as long as p is bigger than 1. Because 5 was bigger than 1. Oh, so you saw, okay, well, hold on, let me tie it all together. And it diverges if p is less than or equal to 1. So it's kind of like a shortcut. I'm going to go back and show you what happened with these ones, and then I'll make up a couple more. I'll just do it in a different color. So when you look at this one, it's a p series. P is 2. 2 is bigger than 1. And so it's going to come out to 1 over p minus 1. 1 over 2 minus 1 would just be 1. And that's what we got. And isn't that a lot shorter? So if you notice that, then you can do that. For this one, what is p? Because it's x to the 1st, right? 1 is less than or equal to 1. So it diverges. And then for this one, P is 5. 5 is greater than 1, so it's going to come out to 1 over 5 minus 1, which would be 1/4. I was going to make up a couple more just to illustrate that a few more times, but it seems like you guys are staring at me like, you cannot have a negative exponent down there because that would actually flip it back up to the numerator. And it only works for 1 to infinity. If you change that, that goes out the window. Now, if P is less than or equal to 1, it'll still diverge. That part's true, but this will not work out because you've changed where the area starts. Does that make sense? Yeah. Yeah, I'm fine with that. P equals 1. Yeah, because you're saying it's a P series. And when we get to the, that's why I'm bringing this up now, because when we get to the infinite series, that's going to be your justification. We're going to do these whole units on does the series converge or does the series diverge? And that's your P series test. So see, I've taught it to you early because it came up. Here, I'll just make up one more. So say you have integral 1 to infinity of 1 over x to the 9th dx. So you would say P equals 9. 9 is bigger than 1. So what is this going to come out to? One over 9 minus 1, 1/8. What if it was 1 to infinity, 1 over square root of x dx? I always like to throw the roots in there because those throw people off. It's still a P series because this is x to the what power? Good. P is a half. A half is less than or equal to 1. And so it diverges. And so you can kind of avoid doing all the rest of that work. So the only difference with this one is I made the lower boundary negative infinity instead of the upper boundary positive infinity. So I'm going to call it A instead of B. Again, I don't care. If you're like, I just want to stick with B, then do that. I just tend to make it A to B. So whatever. So it's going to be limit as A goes to negative infinity, integral from A to negative 1, 1 over x squared dx. And then you're going to do the antiderivative. This limit just hangs out. So that would be negative 1 over x. Again, you would add 1. It's x to the negative second. You would add 1 to that. It would be x to the negative 1 and then divide by a negative 1. So negative 1 over x. You end up doing that one a lot. So you might actually just accidentally end up memorizing it. So you just have to do that one a lot. Such that a to negative 1. And then again, it's going to be upper boundary minus lower boundary. Okay, so your upper boundary, if you plug that in, negatives are going to cancel. It's just going to be 1. Lower boundary, it'll be negative 1 over a. And then your last step is to evaluate the boundary. I know it's negative infinity, not positive infinity. All right, so I know that this is negative infinity and not positive infinity, but it doesn't matter. The denominator is still getting infinitely large. It just means you would be approaching that asymptote from underneath instead of above, but this is still going to go to 0. Okay, so you get 1 minus 0, which would be 1. This problem is the same as number 1 that we did. I'm going to illustrate it for you. This graph 1 over x squared would look like this. What were the boundaries on question 1 that we did? Was 1 to infinity, that would be this amount. And what did we just do here? Negative infinity to negative 1. Now, if the negatives bother you, you could always change it and do 1 to infinity instead, and you'll get the same answer. But it will only work if the graph is what? Symmetric. You have to have that symmetry. But for what it's worth, it's just true. So I figured I would throw that in there. Yes, you have to change it so that that lower boundary is 1 for that to work out though. Like, it actually, thank you for asking that, because that's why I made up this next question, is to illustrate that. So I'm going to change it from a 1 to a 2 and we'll see what happens. That was perfect timing. Because I try to anticipate what you guys are going to ask. I'm like, well, if I was sitting where you are, what would I ask? And then I try to make examples that address those things. Like that's what I attempt to do. It doesn't always work out, but it worked out this time. So yay. All right, let's work it out like we would if we were just going to do the problem. And then I'll show you how you can use the P series kind of formula for it. We'll end up doing this problem twice, but that's okay. Limit as b goes to infinity. Integral from 2 to b 1 over x squared dx. Again, you end up writing the same thing over and over again, but that's okay. That's life sometimes. So then your antiderivative is negative 1 over x such that 2 to b, and then it's upper boundary minus lower boundary. So again, it's no different than doing a regular old antiderivative. You just have that limit hanging out front. So upper boundary would give you negative 1 over b. Lower boundary would give you negative 1/2. This first part, now you evaluate the limit. This first part goes to 0. Negatives cancel, so it'll be plus 1/2. And so you get 1/2. So if you didn't want to do that, if instead you were like, oh, it's a P series, you could do this as 1 to infinity and then subtract out the part that you don't want. So let's think about that. If we want it to be 2 to infinity, but if I change it to 1 to infinity, we would have to subtract out from 1 to 2. And you're probably like, well, how is that any better? Well, it's personal preference. I mean, you could just work out the problem, but if you really want to do like the shortcut trick, you can do this. And then this one is not an improper integral. The boundaries are 1 and 2. This comes down to personal preference, which way you think is easier. But this one, you would be like, oh, P is 2. So it would be 1 over 2 minus 1. And then this one you can just do as a regular old problem. Like it's not an improper integral. This would be negative 1 over x such that 1 to 2. And I'm sorry, the hole punch messed me up there. So these negatives cancel, it'll be plus. So this is 1 plus upper boundary minus lower boundary. So the upper boundary would be 1/2. The lower boundary would be 1. The 1s cancel and you get 1/2. So I don't know, is this one a little bit shorter? Maybe. Again, I'm just showing it to you. It comes down to personal preference, okay? When you do the antiderivative, you have to add 1 to the exponent. So the negative 2 becomes a negative 1. It was the same as the one we did there. Okay, I just have a couple more we're going to look at. So I have 2 more. They'll fit on this paper, or I guess it depends on how small you wrote. All right, so what makes it an improper integral is that the upper boundary is infinity. So it's going to be limit as b goes to infinity, integral from 1 to b of all of this. And then your next step is to do the antiderivative. Think back to some other things I've taught you so far this unit, because there's a special method we're going to need to do this antiderivative. It's going to be integration by parts. Remember the u and the dv, all that stuff, because we have 2 things multiplied together. So u is going to be 1 minus x. And that derivative would be negative 1 dx. So du is negative dx. And then dv is the e to the negative x dx, like the rest of it. Antiderivative. Now e is itself, but what are you going to need out front as that adjustment? A negative. Good. Negative e to the negative x. I think what makes this problem hard is not necessarily the integration by parts. It's just like there's a zillion negative signs. You know what I mean? Like that makes it hard. right, so anyway, do you remember the pattern? It would be u times v. All right, so 1 minus, oh, let me write that limit out front. Don't want to lose that. Limit as b goes to infinity. It'll be 1 minus x times negative e to the negative x minus integral, and then what goes inside of there? V du. Now these two negatives will cancel. So it'll just be e to the negative x dx. Again, what I think is so hard about this problem is the fact that there are so many negative signs. So that limit is still hanging on. Again, if you don't want to write it every time, it's up to you, but don't forget to evaluate it in the last step. For this, we're going to distribute into these parentheses. So it'll be negative e to the negative x plus x e to the negative x. And then again, this antiderivative will be negative e to the negative x. However, those negatives will cancel, such that 1 to b. You're like, why is she torturing us like this? I didn't make up the problem. I just think we should be able to get through it. But something is going to cancel. Do you see it? Yeah, we have a negative e to the negative x and a positive e to the negative x. So thank goodness. But do you ever feel like you caught a break? It's like, oh, good, finally, something went away. So now we're going to do upper boundary minus lower boundary. And again, this comes down to personal preference. I like to fix the negative exponent, bring that back down to the denominator. So I'm going to write it as b over e to the power b. E to the negative x would be in the denominator. So I just put it back in the denominator. And then if you plug in 1, you would have 1 over e to the 1. And then last step, and you're like, thank goodness it's the last step. Evaluate the limit. So as b goes to infinity, what is this part going to go to? That'll be 0 minus 1 over e. All right, I have one more we're going to look at. Okay. Do you need another break before we do that, or are you ready to like finish last one? You're plugging infinity in for b. So this one doesn't even have a b at all, so it just stays. Yeah, e to the 1 is just e. Yeah. Yes, that's so well said. I'm just going to repeat exactly what Evan just said. The denominator exponential increases faster than the numerator. So if the denominator gets extra large, then the whole thing just goes to 0. Correct. Trying to think what note packet I had that on. Hold on 1 second. All right, here it is. An exponential function grows faster than a polynomial. A polynomial is like x squared, x to the third, x to the fourth, x to the fifth, whatever. So an exponential is going to grow faster than a polynomial, which grows faster than a logarithmic. So it's like who's in charge here. The exponential is going to grow so much quicker that it's going to go to 0. I'm glad you brought that up though, because we just got to review limits. Then it would go to infinity, and then what would our answer be? Dies, diverges. Please don't put dies on the AP exam. Oh, diverges. Well, yeah, like the movie. It's fine. I don't care. I'm gonna mark it right. But yeah, what we're headed towards, like close to the end of this class, there's going to be 2 whole units on infinite series, and it's always, does the series converge or does the series diverge? And there's like 10 different tests that you have to learn, and the p-series test is one of them. So look, you learned one of them. Again, the problem is the sheer quantity of information. I'm going to do my best to get you through. All right, this one is from negative infinity to positive infinity, which I think is just cool. You have to break it somewhere. Where should we break it? 0. Break it at 0 if you get a choice, which you do get a choice. So we're going to do negative infinity to 0 of this thing. plus 0 to infinity of that exact same thing. So as a heads up, we're now doing 2 problems instead of 1, and they're both the same. So you're going to write the same thing over and over again for this one. That's okay. Just, keep track of what you got. So for this one, I'm going to use a, since it's the lower boundary. Limit as a goes to negative infinity. Integral from a to 0 of that stuff. And then the other one, I'm going to use b since it's the upper boundary. Again, I don't care. Whatever letter of the alphabet you want to use is cool. Your next step is to do an antiderivative. This is one of the patterns that we looked at. And again, I like doing this because I keep on trying to review everything that we've looked at before. Does it jog your memory? I'll tell you if we've all forgotten. It is arctangent. Good. A is going to be what? 4. Good. U is just x. So du is dx. And then there's no adjustment that you need to do. All right, so this will be limit as a goes to negative infinity. Arctangent pattern, it'll be 1 over a, so 1/4 arctangent u over a, so x over 4, and then such that a to 0. Plus, and then you're pretty much going to write that over again. Which, again, I'm going to write it. I'm not going to have an argument with you. If you're like, I can see it right there, I don't need to write it again, fine. I'm going to write it twice. I know myself, you know yourself, I know myself, I'll lose track of it if I don't write it, so I'm going to. So then it's upper boundary minus lower boundary. And I'm going to draw a little picture of tangent off to the side. Graphing the trig functions was something that you guys missed out on. So this is going to be a little tougher for you. You're at a bit of a disadvantage. Tangent has an asymptote at pi over 2 and negative pi over 2. And then it looks like this. And then there's infinite wiggles. Do you know what I'm saying? We only really need to look at this one, but it would keep on going and there would be more asymptotes infinitely forever and ever. It's funny, we're doing the rational graphs in pre-calc right now, and I did graphs that have 2 vertical asymptotes, and it was like, oh my gosh, there's 2 of them. I'm like, don't even ask me about tangent. There's an infinite number of them. Anyway, so upper boundary, if you plug in 0, I know this says arctangent, but it works both ways. Tangent of 0 is 0, so arctangent of 0 is 0. So that one's kind of nice. And then plug in a. So it will just be 1/4 arctangent a over 4. I kind of didn't leave enough space for that one. That was stupid. All right, plus limit as b goes to infinity, upper boundary minus lower boundary. If you plug in b, you're going to just have 1/4 arctangent. Oh, I didn't learn my lesson. Of b over 4 minus, and then your lower boundary, when you plug in 0, arctangent of 0 is just going to be 0. So that's nice. The zeros, like you can just pretty much ignore those, they're gone. And then your last step is to evaluate the limit. So watch me point to this. We're going to negative infinity for arctangent. Going to negative infinity happens at negative pi over 2. Does that make sense? That's because we're doing it backwards. I drew tangent, but we're doing arctangent. Okay, so it's going to be negative 1/4 times negative pi over 2. If you were like, hey, I didn't quite get that, I'm about to do it again. Here, if you're going to infinity, that's going upwards, that's this part right here, that happens at positive pi over 2. So it'll be 1/4 times positive pi over 2. So these negatives cancel. So this will be pi over 8 plus another pi over 8, which will be pi over 4. I'm not going to do any more problems, but I am just going to show you a trick in the calculator. It's highly likely that they would put these on the non-calculator section, but just for what it's worth, you can kind of like, not always, but kind of like get the answer. For example, math 9, if you math 9 this, if you go from 1 to infinity, now you can't put in infinity, but if you put 1,000 and then put in here 1 over x squared, it'll be like close. Sometimes these take a minute, but we know the answer is 1, but see, it comes out 0.999. They'll all work out like that. Like it'll be close. Again, I think they'll probably put it on the non-calculator section, so that wouldn't really help in any way. But I mean, for what it's worth, you can do that. Here's the only thing. It'll lie to you about the ones that diverge. It'll give you an answer, even like, see, watch, where's one that diverges? This one. So if you do 1 to 1,000 for 1 over x dx, see, like this will give us an answer, right? Because it's not actually infinity, so it's only doing from 0 to 1,000, and they take a while because the calculator gets confused. It's like, what on earth? But it will come up. Oh, what happened? Oh no, it didn't give us that one. Oh, I did. I put 0. Oh, thank you. I'm sorry. There we go. See, it gives an answer, but we know that it diverges. So you have to be careful with it. But for what it's worth, you can do that in the calculator as like a little bit of a workaround or a check.